This is going to be the lecture over Chapter 3, Sections 1 through 7. So we'll go from basic properties of nuclei all the way down to radioactivity. So let's take a look at what we have here. So radioactive materials are commonly used to deliver radiation for therapeutic purposes. It's essential to have a detailed understanding of radioactivity. If you place radioactive material inside or on the surface of the body, it's considered to be brachytherapy. If we use radioactive material to produce a beam of radiation that's applied externally to the patient, that is called external beam therapy or teletherapy. So here we have some basic properties of nuclei. We all know that the nucleus is a dense, positively charged body that consists of neutrons and protons. Referring to both of them together, we have a term called nucleons. The mass of a neutron and the mass of a proton are pretty close, not exactly the same, but pretty close. And the mass of an electron is about 2,000 times less, or the mass of a nucleon is approximately 2,000 times more than that of an electron. Your notation here is going to be your chemical element with the nucleon count up here represented by A. The proton count is going to be down here represented by Z. So you could have hydrogen, which just has one proton in it if you're looking at representing the element that way. You've got helium here, which has 4 nucleons, 2 of which are going to be protons. And you have cobalt-60, in which case 27 of those are going to be protons. So the chemical identity is determined by the number of protons in the nucleus. Under normal conditions, an atom is electrically neutral, and therefore the number of electrons are going to equal the number of protons. And it's the number of electrons in an atom that determine its chemical behavior. 2 atomic nuclei with the same number of protons but a different number of neutrons are going to be called isotopes. Hydrogen has 3 isotopes. Ordinarily, the ordinary light hydrogen is going to be represented this way. That's what you see the most of. Deuterium is going to be represented this way, where you've actually got a neutron in along with a proton. And tritium, where you have 2 neutrons in with the proton. And they are considered to be heavy hydrogen. Deuterium, well, you can see the nucleus of the deuterium atom is also called the deuteron. Deuterium occurs naturally in water in low concentration, and when 2 deuterium atoms combine with an oxygen atom, the product is a type of water that is slightly heavier than normal. It's called heavy water. Tritium has 1 proton and 2 neutrons. It's radioactive and does not occur naturally. Cobalt-59 is non-radioactive, but cobalt-60 is a radioactive isotope. The uranium that is found naturally in pitchblende is a mixture of isotopes. Uranium-235 is the isotope that readily undergoes nuclear fission, and 238 is the predominant occurring isotope and does not readily undergo fission. So you've got some definitions here. Isobar has the same nucleon value but different Z values. Isomer has the same A and Z values, but the nucleon is in a different energy state, an excited state. So an isomer example might be technetium-99M, where this is considered to be metastable. And then you've got isotone, in which you've got the same number of neutrons. The way I remember that isotone, the N there refers to neutrons. If you go back and look at isotope, which is right here, then the P there signals the same number of protons. And that's how I remember it. And then you can see the all of that summed up here in the memory aid. All right, you've got four fundamental forces of nature. The gravitational being the weakest, then you've got the weak nuclear, then you've got the electric magnetic, and then you've got the strong nuclear. So you can see the strength gets stronger as you go from 1 to 4. These two and 4, really manifest themselves in the nucleus, and 1 and 3 are what we see that are outside of the nucleus. If you ever get to the point where you are bored and you really want to waste some time, try looking for what they consider to be the holy grail of physics, which is an all-encompassing unified field theory that describes all 4 forces within a single framework. Very difficult thing to do, and a lot of people have spent a lot of time thinking about that. So the modern theory of gravitation is the general theory of relativity developed by Einstein in the early 1900s. He spent a lot of time trying to figure out how to unify a lot of forces. So there's now a successful unified theory of electromagnetism in the weak force called the electroweak theory. The theory of the strong nuclear force is called quantum chromodynamics. The electroweak theory, together with the quantum chromodynamics, is referred to as the standard model. The theories put forward as candidates to combine these into a single theory is the grand unified theory, or GUT for short. Grand unified theories do not incorporate gravitation. In recent years, the class of quantum theories called string theory has emerged that does include gravitation. The equations of general relativity arise quite naturally from the equations of string theory. And in string theory, elementary particles such as the electron are viewed as one-dimensional structures rather than point objects. Mathematics is, yeah, I'm sure it's pretty bad, and it is not yet possible to work out the full implications of the equations. So when it comes to binding together particles within the nucleus, we come up with something here called a mass defect. So the mass of atomic particles may be expressed in AMUs, or atomic mass units, where that is defined as 1/12 of the mass of a carbon-12 atom. And it says the atom, not the nucleus. This mass is equal to 1.66 times 10 to the minus 27th kilograms. And it corresponds to an energy of about 931 MeV. So 1 U is roughly the mass of a single nucleon. And the mass of a proton is about 1.00727 U's. The mass of a neutron is just a little bit more. If you go to a deuterium nucleus, you can see here that it consists of a proton and a neutron. It's a simple composite nucleus. And we're going to compare the mass of a free neutron plus the mass of a free proton to the mass of a deuteron. So we know the mass of a deuteron happens to be this. If you add the individual particles together, it ends up being that. So what's the difference? We're noticing here that the mass of the deuteron is less than that. This is what's called the mass defect. It suggests that some energy is needed to separate the deuteron into independent free particles. And this is called the binding energy of the nucleus. So let's compute the binding energy for a deuteron by first determining the difference in mass between the deuteron and the free proton and neutron. This is the free proton and neutron. This is the mass of the deuteron. The difference between the two is this. And since 1 AMU corresponds to 931 MeV, then the change in energy here is 2.3 MeV. The minus sign signifies that energy has to be absorbed by a deuteron to separate it into 2 free particles. And this is the amount of energy that you can get out when you compare a neutron and a proton to make a deuteron, or conversely, the amount of energy that you must put in to separate those two. And this demonstrates that energies associated with nuclei are on the order of mega electron volts, or MeV. So you can compare this with energies that are associated with atomic electrons, which are on the order of EV. Chemical reactions involve transfer or sharing of electrons between atoms. The energies associated with chemical reactions are on the order of electron volts. Energies associated with nuclear reactions are approximately 1 million times larger than the energies associated with chemical reactions. And this accounts for the fact that nuclear weapons have approximately 1 million times the explosive energy of chemical explosives. It'll make you feel all warm and fuzzy. Stability of nuclei. So we can generalize the previous discussion of binding energy of the deuteron. So we're going to let this expression equal the mass of an atomic nucleus of nuclear number A and atomic number Z. M sub P is going to be the mass of a free proton, and M sub N is going to be the mass of a free neutron. So in general, the binding energy of a nucleus characterized by A and Z with A minus Z neutrons is going to be this. So basically, the change in energy is going to be the mass of the atom or the nucleus that we're looking at, and then minus Z times the mass of the proton minus what would be N times the mass of the neutron, and we multiply that by the speed of light squared. And yes, this will end up having a negative value because this mass and this mass is going to be greater than when they're combined into a nucleus. So if we take the change in energy here, which that's what the delta means, the change in energy, and we divide it by the number of nucleons and the average binding energy per nucleon, we get a graph, and it's going to be the curve of the binding energy. In other words, this. And what you're noticing here is that it doesn't quite get to 9, the average energy per nucleon, average binding energy per nucleon, doesn't quite get to 9. It sort of tops out here around iron and then just kind of drifts slowly off. And you can see here as the number of nucleons continue to increase, you can see that there's a limit there that we can't go past. So to combine these two nuclei, well, let me step back. If like nuclei could be made to combine, the average binding energy of the resulting nucleus would be greater, leaving excess energy to be released. And that process, nuclear fission, does naturally occur in stars. To combine two nuclei in this way requires them to come close enough for the nuclear force to provide the glue to hold them together. As nuclei are positively charged, they repel one another, and therefore high speeds are required to overcome the Coulomb repulsion. The nuclei in the high temperature gas travels at high speeds. If the temperature is sufficiently high, the nuclei can approach each other closely enough that there is a significant chance the short-range nuclear force can overcome the long-range Coulomb repulsion, and then fusion will occur. This is the process that provides energy for stars. In the sun, a series of fusion reactions combine hydrogen to form helium. This energy has been released on Earth in the form of a hydrogen bomb. If a nucleus with atomic number beyond 56 were to split into two smaller nuclei, the two smaller nuclei would have a higher average binding energy per nucleon, and therefore energy would be released. This process is called nuclear fission. So when they split apart, it's fission. When they come together, that's fusion. Energy from nuclear fission is released from uranium in a nuclear reactor under controlled conditions. Energy is released explosively from fissions in an atomic bomb. In other words, there's no way to control it. Nature attempts to minimize the change in energy. In other words, make it as negative possible. This sometimes manifests itself as a spontaneous transformation of one nucleus into another with lower binding energy. The excess energy is emitted as radiation, so the process is called radioactive decay. The resulting nucleus, called the daughter, is more tightly bound. Nuclei that do not undergo radioactive decay are said to be stable. This graph is here to show you that as you have a nucleus that increases in the number of neutrons and increases in the number of protons, that as you increase that value, and this line here shows you when the two numbers are equal to each other. As you put more and more nucleons into the nucleus, what happens is that you end up having more you have more neutrons in the nucleus in order to be able to make the atom stable. And that's why it's got this bend here. You've got to be able to separate those protons as much as you can in order to be able, but still hold the atom together. So that's what this graph is showing, is that as you go further up, you're basically ending up with a greater number of neutrons needed as you increase the number of protons. So for Z greater than 20, Z is less than N for stability. So you can see here in this particular graph that the number of stable nuclei with an even number here greatly outweighs when either one of these two values are odd or when both are odd. As a matter of fact, when both are odd, the number of stable nuclei is rather small. And in both of these cases, where either the neutron is even or the proton is even there, you don't come close to approximating it when both of these are equal to each other, or not equal to each other, but both are even. Okay, so now discussing antimatter. In 1928, you had an English physicist, Paul Dirac, who formulated a relativistic theory of quantum mechanics. The Dirac equation seems to suggest the evidence of positively charged electrons. And at that point, it was pretty radical to suggest such a thing. So it wasn't clear what this meant until the discovery of a new type of matter called antimatter in 1932. In that year, positrons were discovered by Carl Anderson. The discovery was made while Anderson was studying cosmic rays, which are high energy charged particles, mostly protons, that bombard the Earth. Cosmic rays interact with atomic nuclei, producing a shower of secondary particles. Among those particles, you see that positrons are found. The positron can be described as an anti-electron. Basically, it's around the same size as an electron, but it's just got a positive charge to it. Its mass is identical, and as I said here, the charge is exactly equal in magnitude, but opposite in sign. When a positron meets an electron, they both disappear and annihilate, leaving behind two gamma ray photons. The symbol for an electron is E, or beta with a minus, and for a positron, it's E with a plus sign or beta with a plus sign. The annihilation reaction is written this way. Basically, you've got your positron plus the electron, and you end up with two gamma rays. And this is an example of a complete conversion of matter into energy as described by Einstein's equation. Charge is conserved because the net charge before and after is zero. Each gamma ray has an energy of 0.511 MeV, and the total energy of the two gamma photons is equal to the rest mass energy of the positron plus the electron. So in other words, the energy that you get out of this is the same as calibrating the mass for these into producing energy. So the gamma radiation is called annihilation irradiation. The gamma photons travel in opposite directions, and the reason they do that is to conserve momentum. It is now known that every particle has an antiparticle, even neutral particles. If a particle has an electric charge, its antiparticle has a charge of the opposite sign. When the particle meets its antiparticle, they annihilate and form gamma photons. So there we go. Now 3.6, Let's take a look at the table. So you've got an electron, or whatever the name of the particle happens to be. You've got the symbol for it, depending on how it needs to be written. And then you've got the charge. What is the charge of each of these? You've got the rest mass, you've got the rest energy, and then some comments regarding each of these. So you've got the electron and the positron. You'll notice the comparisons between the two, the charge, mass, and the rest energy. You've got a proton, and then you've got a neutron. These aren't opposite particles, but you can see some of the similarities here. You've got the deuteron, you've got an alpha particle, you've got a neutrino, and pi mesons or pions, which are interesting all unto themselves. But all of that leads into the concept of radioactivity. And this results when unstable nuclei attempt to minimize their energy, thus becoming more tightly bound. So the parent nucleus undergoes a spontaneous transformation into a daughter nucleus. And all elements with Z greater than 83 are radioactive. Then there are three main types of radiation that are emitted when a nucleus undergoes radioactive decay. So you've got gamma rays, and these are high energy photons, and photons don't really carry a charge. Any photon emitted by nuclei or in the electron-positron annihilation are called gamma rays. High energy photons from other sources are called X-rays. Note that the distinction is one of the origin, but not necessarily the energy. An X-ray photon may have more energy than a gamma ray photon or vice versa. But again, any photon emitted by nuclei or in electron-positron annihilation are called gamma rays. That's how they originate. High energy photons from other sources are just considered to be X-rays. So that's gamma ray radiation. Alpha particles are basically helium nuclei. These particles only travel a short distance in matter, just simply because they're pretty heavy. Beta particles are either electrons or positrons. Positrons and neutrons are generally not spontaneously emitted from nuclei. Radioactive nuclei can occur naturally, or they can be produced artificially in a particle accelerator or a nuclear reactor. And we'll discuss the sources of those a bit later.